All right, good afternoon, everyone. Thank you for joining us today and attending the Manual D webinar. This is the last webinar before the holiday break, so thanks for joining us. It will be recorded, and the recording is sent out to all attendees in a Google Drive link. But if there are any issues with audio right now, please let me know. My name is Erica DeLello. I'm a project manager for Noresco. This series is sponsored by the Colorado Energy Office with training materials created by Colorado Code Consulting. We've been working with the Colorado Energy Office to provide trainings just like this one. As you can see here, we have a list of the upcoming trainings into the new year. So if you have any interest in registering for another webinar, in the follow-up email, you'll have a link for that for the registrations. Also, we're offering tailored group trainings or technical assistance for jurisdictions that are updating I-codes. So feel free to reach out to me if you have any questions about that. Yeah. And then in addition to that, we've put together a code adoption toolkit that reviews cost implications of changing code cycles, the benefits, and other compliance resources. We've also created within that code adoption toolkit a troubleshooting guide that covers I-code conflicts, alignments, clarifications, and passive compliance. This will also be updated. Currently, it's mainly focused on 2018, but it will be updated for or have content in addition to 2018, we'll have IECC 2021. So check those out in the new year too. And throughout this webinar, we do want to encourage questions. So please use the Q&A function and I'll let Gil know at the end of the presentation. The chat window is available to chat among the participants. Please use the Q&A if you'd like to ask a question. There's also the ability to raise your hand. And at the end of the presentation, I can unmute you so you can ask Gil any question you'd like. And then lastly, there is a survey window that will pop up following the webinar. Please take a minute to fill out that feedback so we can continue to improve. I've been sending Gil all of your comments. So, so with that, today's presenter is Gil Ross Miller. He's been in the construction industry for over 40 years. He was the chief building official for Parker, Colorado from 2003 to 2016. He served on numerous committees that I've listed off in previous webinars that he's currently serving on the IECC 2024 Correlation Committee. So yeah, we've already started looking at 2024. Yeah, he's a guy that will have answers to a lot of your questions. So with that, I'll let him take it from here.
All right, thanks, Erica. Let's see, I need to share my screen. Let's see, should be that one. All right, should be seeing it now. We good?
Yep, we're good.
Excellent. All right. All right, folks, we'll get started here. So Manual D, so we've been down the path here, yes? We've done our Manual J, heat gain and heat loss calculations. Last week we did our Manual S, was picking our equipment. Now that we've picked our equipment, we know the furnace size and we know what it's capable to do, the CFM that it can do. Now we get to design the ducts themselves. It's kind of an important spot, right? Got to figure out how much room with CFM we need to each room, eh? And that's how it's done, room to rooms, I call it. So yeah, so Manual D gives us these design parameters that will actually, at least on paper, and generally works, yes, to get all these CFM, room-to-room CFMs, okay? So we don't want, right, undersized duct work. We're not going to get the temperature rise we need, and that was something we talked about quite extensively, because temperature rise is a big deal. The temperature rise is correct on your furnace, you're actually getting the BTUs that we think you're getting. Absolutely. The output capacity, which we talked about last week. Yeah, undersized ductwork, that's not going to happen. Freezing coils, those of you that have had issues with that or have dealt with that in the past, it's because air conditioners not getting enough air, number one, never has. And number two, they've always been twice the size. So we kind of solved that last week by getting the proper size. Yeah, efficiency absolutely is not nearly as efficient, not working as designed. And of course, you've got too small a ductwork. You can actually, you hear the whistling, right? You hear the air moving. Reasonably well-designed system, you're not going to hear the air moving. You shouldn't hear it. You shouldn't hear it blowing out. You shouldn't hear the return airs, sucking air within an inch of its life. You should just kind of, right? Maybe a little light fan or a little noise in the background, and you really have to listen for it to hear it. So this is where we were at last week, yes? Last couple of weeks, we've kind of decided all of this business. And now we're starting to get down in here. We're going to discover how this whole, static pressure thing relates to everything, okay? How I even came up with 0.7 and what it even means and how that relates to what we're doing. I've talked about this hopefully the last couple of times. This manual RS is awesome piece, talks, great, easy read. Go to the ACA, Air Conditioning Contractors of America, great standards. It's a contractors association, but they're also a standards writing organization. And this is a nice, relatively inexpensive book that goes through some wonderful things. How ACs work, heat pumps, all kinds of wonderful stuff. And it's good plain language stuff. The other thing that it talks about in there are these single zone systems. And we're talking about zoning today a little bit and the ductwork design itself. Now, the beauty of it is this is just one little piece of table that's within Manual RS. And it actually starts to say what are the expectations for that single zone constant volume system. So a lot of times we have a basement, a first floor and a second floor, but we got one furnace in the basement. And when it's on, it's heating or cooling the entire house. And when it's off, it's not doing anything. So the idea here is it's saying, okay, well, during the heating season, what are the expectations based on humidity or thermostats or room to room or floor to floor temperatures? And we had a few examples of that where during the cooling season, if it's a design day there at 90 degrees, say there in Colorado, you might expect up to 6 degrees between the first and the second floor. Hopefully I told you that story about the temperatures that we set around the place. And we had really high temperatures that year. It was 105 degrees outside. Well, believe me, there was a 10-degree difference between the first floor and the second floor, easy on those days. And the system was working exactly how it was designed, okay? So just because it's a little warm upstairs doesn't mean the system wasn't working. It works just exactly the way they designed it. So zoning really needs to be not really a code requirement, but it's certainly a best practice when it comes down to comfort type things, because we don't describe comfort in the code, do we? We don't touch it with a 10-foot pole in any way, shape, or form. So RS has a whole chapter on comfort and what that is and isn't. Okay? So just a couple examples here. So if I'm looking at, if this is we have a basement level here, maybe first floor and a second floor, maybe an attic, just for the heck of it. We'll say it's a habitable attic. So I'd have 1, 2, 3, 4 zones in this house. If I were designing it, very technically per Manual D and RS, that's a four zone house. Okay, yeah, because you suppose it might get a little hotter up here. Yeah, in the summer, you bet. Yeah, it's going to need different requirements in this level, isn't it? Again, more of a best practice. Where if you got this nice, perhaps slab on grade or on a crawl space, nice little ranch house. That's a one zone house. There's just one level. Might like a 2-zone house if it's a bigger ranch style house, and bedroom area and living area might be one. So let's see what we got. So this is kind of the steps. So first we determine the CFM flow to each room. We're going to make a rough sketch of the duct runs and the supplies, and using the framing plans is a good idea. Avoid those steel I-beams and things, micro lambs you can't cut through. Then we collect all our blowing and air side pressure drops. What's in the way of the air moving. The coil, AC coil, maybe air filters, registers, grills, balancing dampers, things of that nature. Then we would determine our total equivalent length of the ductwork. And that essentially is the longest supply path plus the longest return path, and that is the linear footage, yes, the distance of the ducts, plus the fittings themselves. Then we actually can then determine our friction rate after we know what our available static pressure is. And then we size all the ductwork based on the CFM, the needed flow that we need, and the friction rate, and we're done. Any questions so far, or are we good? No? All right, we'll go through each one, just being a smart aleck there. Yeah, so if you look at the manual D, and it's, it actually says best practice would have some balancing dampers. It isn't too heavy on that. You're going to find that a lot of builders don't use them. A lot of designers won't put them in. It's the best for balancing, but many of them are just doing it based on the size of the duct, right? So a 6-inch duct is going to carry a lot more air than a 4-inch duct, for instance, and that's how they quote balance the system. So it's not something that I require, not something the code really requires, and Manual D just makes a nice suggestion, says, you know what, it's great if you do, but we're not going to yell at you too bad if you don't. Okay. So I've got guys that do and guys that don't, either one. So here we've got kind of a not really a, I guess, best practice it would be. Your total system flow would be about 5% of the design flow, because everything we've done so far has just been math and stuff on paper. Okay, when we get out into the real world, things are change. Yeah, and they don't work like the paper says it should. So we've got to be somewhat lenient. It's not going to be perfect in any way, shape, or form, but it is certainly going to provide and perform as we expect. Okay. Right, room to room flows are going to be within 10, plus or minus 10 and up to even 20%. A lot of guys are putting in supply airs that are going to very small rooms like master closets or bathrooms, right, that might be fairly small. And if they're in an interior room, they have no exterior walls, the manual, the amount of CFM needed to condition that room might be 4 or 5 CFM, really, really small. That's really tough to get ductwork and things that only give you 5 CFM. That's hard. Your total system static, which we'll get into, will be with about 1/10 of an inch of water column, and duct velocities, and that's the thing that makes the noise. That's what you hear, are within what we call Manual D recommendations. The beauty of it is, now this is just a table I recreated out of Manual D. Kind of gives you basically some recommendations on what supply side and return side velocity should be. Okay, so we got trunk and branch ducts and our face velocity for the actual registers and return grills. And then, are we using rigid duct? Are we using flex duct? And some, recommended places and the most you should have. And if you stick within the recommended areas when you're designing, you're going to end up with a system that works like it should. Okay, statics are not going to be excessive. The furnace isn't going to sound like it's about to collapse. You don't even hardly hear it run, and you're not going to hear a lot of noise in your rooms. Here's the beauty of it is this is just a screenshot from the RightSoft software where you can actually then input all of this. So the designer can go in and say, hey, what's my minimum and maximum velocity that I want in my design? Is it, we got all the different types of material, sheet metal, you hit this little button, a big drop down comes on and say, what kind of material you're using for it, maximum duct height, for instance, if it's in the basement, you don't want it any taller than the I-beam that's dropped generally. So there's a lot of different parameters that they can set, for supply and return. Insulation, the register shape and the type of it is and where it's at. The duct layout itself, there's a lot of different ways you can do that. User defined just means I can move the ducts wherever I want. This piece down here, not that the code really says anything about it, but you start to wonder, how do you know when you need one supply outlet or you need two in a room or three? Well, this is a default within the system, and it's just a recommendation for Manual D. I don't know that many designers had actually changed this, but what that's saying is that in heating, the maximum supply boot, SB, is going to give me 8,000 BTUs of heat. And cooling, it's going to be 4,000 BTUs of cooling. So once a room reaches that point, it will automatically put in another duct, put in another supply duct in, okay? We'll talk about this wonderful thing here, automatic trunk reduction. We'll talk about that. And this variable friction rate is also very nice. This design, I didn't happen to use bi-level zoning, but it's very sophisticated. It really helps you design the ducts quite a bit. Helps you a lot, especially this variable friction rate and this trunk reduction, which we'll talk about and what that means and is and all about. So essentially, the required CFM to each room is relative to the room's calculated load. Makes sense, yeah? Essentially, if the room, right, needs about 5% of the cooling capacity or heating capacity, it needs about 5% of the CFM. Now there's a little bit better way to do it. So this is how this is the math behind it, okay? And it's just math, and is a really good way to point out that this is just math in real life can change things, okay? So we're not going to go through the math, but essentially takes the structure loads here for heating and cooling. I don't know why my thing is in black. And then it's just basically math. So my heating flow factor is this 830 CFM divided by this 26,853, which is the structure load. And it gives me this heating factor of a 0.031. All that number means is that it takes that number times the BTUs required for that room, and then that equals the CFM that you need in that room. Okay, that's all it's doing. It's just the math. Now we talked about this quite a bit, didn't we? This 830 CFM and how we even got that to begin with. As you remember last week, we went into the fan chart, the fan speed chart, and we found out what the heat speed was, didn't we? Yes, it was shipped on medium high or medium low for the heat speed. That then gave us also this number here, didn't it, too, this temperature rise. And I said, that seemed a little high. You'd want to get more toward the middle of the temperature rise range. So I said, we might want to increase this up another speed to get this number down. So you see I think you see where I'm going with this. Well, let's say you've got all this said and done and you had it all good. And then you get out in the field and say, gosh, yeah, it's running too hot. It's not moving this 830 CFM, because we also talked about how those fan speed charts are developed at sea level. And that fans, the way they work, scoop in the air, yes, doesn't work as well in altitude because the air is less dense. So it's not scooping as much air each time it moves around the circle there. So what we found in the field is we actually had to take that and notch it up a speed or two. So if my original plan said I needed 50 CFM to a room, as an example, but all of a sudden I take that 830 and I jump it to 1200, as an example, what's going to change? You know, the room-to-room CFM will certainly change. Absolutely, positively. Usually it's not that extreme. I guess what I'm saying is for your jurisdictions that are getting actually doing room-to-room flows at final, okay, and you're finding that they're off, it could be as simple as going back and changing that CFM number right there, and then boom, software does the rest. Okay, I have not found yet that changing this downstream after all the ductwork's in it changes the ductwork design in a substantial manner. Okay, you'd really have to change that. You'd have to double that CFM to make any dramatic changes in the ductwork. Would it change slightly? Yes. Is it going to affect the performance? I would say 99% of the time it would not. It was in those rare cases where you would have to change it dramatically. Again, for those designers that are kind of getting bent out of shape, or jurisdictions that are pounding you because it's not matching the manual J, well, just go change the CFM and resubmit and move on with life. Because all that math will change because we changed this number here. Okay, because we had to get the temperature rise correct. That's the key. Yes. All right. Hopefully that makes some sense. All right. So that's how we got room-to-room CFM. So yeah, so the RightSoft or Elite or whoever you're getting the software actually does a lot of work for you. And we'll show you later that you don't actually have to use the software to design your ductwork. You can do it by hand. You can actually draw your own duct plan, do your own sizing. You don't have to use the software. You can all do it by hand. We'll give you an example here later. We won't have time to work through it, but we'll show you how it's done. So how did we end up with 0.7 inches of water column? That's where we started. Well, it's the designer's best guess. They got to start somewhere. This just happened to work. Okay. So what this is saying is that, remember, in our fan speed chart, we said, okay, if at a 0.7 total external static, it would move that 800 CFM for heat, for instance. Okay. So that's total. So what we need to do is we got to enter everything in there that is in the way of the air moving. What are we putting in the way? What is within the ductwork that's going to inhibit the air from moving? Well, the AC coil is one of them, is it not? You put it right in the middle of the furnace, yeah, and the air's got to move through it. Heat exchangers. Now, for this furnace, the heat exchanger for the heat was already in the furnace when they did the testing, so we don't have to add it. If this was simply an air handler, we would have to add any coils that were added into that unit, okay? In this particular case, we don't have to because it was already in the unit when it was tested for airspeed, right, CFM. Then we would actually enter, right, our supply registers and return grill resistance, because we're putting it in the way, right? That's the grills at the end of the supply air and the return air. 0.03 is an acceptable standard to use. Manual T, which is something we haven't talked about, gets into very fine detail about resistance to grills, register grills, and return register, supply registers and return grills. Different manufacturers and throws, we're not going to get into it today, but 0.03 is an accepted standard, let's say. Filters. I always recommend that designers put in at least a 0.1 for filters and more if they've got electronic filters, something like that, options that they're going to be putting in. Because a lot of the performance data, in fact, the ones that we looked at last week, actually said that it included the filter, okay? But the filter they're using is, well, let's say, extraordinarily cost effective. Yeah, it's the cheapest thing on the planet. If we're putting on humidifiers, anything like that, manufacturer's performance data, if we're using balancing dampers, you could use the same 0.03 for those. Anything else, whatever else we're putting in the way. Hey, the beauty of it is this is not just a screenshot from the software. Elite and Writes Off actually do a report that gives you these this detail. So up here, what it does, right? We're starting with the 0.7. Then we come down to the coil. That's our conditioning coil. I've just used 0.25 for both. Some designers, this would be what they call a dry coil. And this is what they would call a wet coil because, right? Warm, moist air condensing on the coil makes it wet and has sometimes a little bit higher resistance. If I see the same here, I don't lose any sleep, especially in your climate zone, very dry. You could use dry coil in both and it's not going to affect anything. Heat exchanger, we don't have anything going on, right? We got the 0.03 for our supply, return. I put in a filter. I said we didn't have any humidifier, no other dampers. What this is saying is now that we started with this 0.7, we have to subtract all of these because it's already in the way. What we have here is what's left over to design the ductwork. So when I said available static pressure, well, that's this number here. In this particular case, it's a 0.29. So we're going to find out, is that enough for the length and everything that we've got for ductwork? So what we've got here is we've got measured length of runout in both supply and returns. And what that is the runout. So from where it connects to the trunk to wherever the supply is. Okay. The measured length of trunk is the distance from the furnace. So that the furnace is here to here. Okay, that's the trunk. And this is how long the air thinks the fittings are. And we'll talk about fittings here. And adds to my total equivalent length. So in this case, we had 190 for supply, 115 for return. That gave us a total length of how long the air thinks it is to get from one end of the system to the other, 305 feet. Now that we know our available static pressure and our total equivalent length, we can come up with this friction rate. And I'll show you the math here on the next slide. So the friction rate, just think of the friction rate as the relationship between the furnace blower and the ductwork. Okay? That friction rate has got to be between a 0.06 and a 0.18 because there can be not enough pressure in the ducts to get it to work, and there can be too much pressure in the ducts and they won't work. Okay, so on paper we've got to get within this range. So essentially what we do here is just math, right? We have our available static pressure, which is our 0.29. The friction rate is always done in 100 feet of duct. That's where all the tables are set up. And then total equivalent length is at 305. So we got 20.29 times 100 divided by 305 gives us this 0.095, which, amazingly enough, is between a 0.06 and a 0.18. Is it not? Yes, that's a good thing. So this is just something, this is our friction rate charts right on manual D. And it tells you what's happening here. So here's the sweet range right in here, 0.1. Wouldn't that be nice if it was all 0.1? But that's rarely the case. Most of the time I'm these really long ductworks, I'm getting, 0.06, 0.07. They're, getting into danger zone here. So if it's too low, right, we got to increase speed, change the blower, or decrease my total equivalent length. Here, too high, yeah, not too much oomph, too much speed, too much CFM, or make the ductwork longer, put some bad fittings in, something. Typically, this is not the issue. This is the issue, typically. Usually it's too low, not too high. Generally, not always, but typically. Okay, so here, it is starting to tell you what's happening. So this is just out of writes off. This is starting to tell you at least something that's going on. So 0.7 and a pressure losses of a 0.41 certainly looks reasonable. We just saw what was going on. So if they're not giving you one of these, and this tells you, oh, let's see, where is it? Oh, here, excuse me, here. So Writes Off and Elite, you both got this, where it actually tells you what the designer input for each of these items, instead of having to give you a screenshot. Okay. This way you can at least know that they got everything in there and in place. Okay. So from these, you can't really tell except, the pressure loss. Now I've seen a lot where they'll say, oh, the external static pressure is like a 0.5. There are no pressure losses and my available static pressure is 0.5. Clearly that is wrong. It's absolutely wrong. They're always going to have a coil. They're always going to have, right, registers and grills, and they're always going to have a filter. Now I say if they don't give you a filter, right, they don't give you a filter number here, I don't nix them for it. I don't fail them for it. I just simply say, you may consider adding a 0.1 for filters, because what do folks generally do? The first thing they're going to do is run out and buy that Filtrete filter that isn't very thick, and they cram it into their furnace and wonder why the air conditioning and heat doesn't work as well. Well, it's because we didn't add any static for it, and it's got a static pressure that's as bad as the coil. Right? So you got to beware. I mean, it's just, like I say, a word to the wise, kind of a best practice piece. I haven't lost anybody yet, have I? Here again is what they're giving you, this piece here. And I think we have, yeah, I just made a close-up of it. I don't know that maybe Elite doesn't have one. I can't remember. Those of you that are using Elite, you can tell me if they do a piece by piece pressure loss, right? So 0.236, that seems pretty low. It's possible if this is a really small system, it all depends on the coil. Coil is usually the biggest piece of it, and some of them can be pretty low. I used a 0.25, but there are a lot of them that are a 0.15. Depending on the size of the coil, 0.16, that's not that unusual. But if you get something that's much lower than this, I would ask and say, well, gee, the static losses seem kind of low. Might want to, what did you actually use? Yeah, you can see what this one is, right? Total effective length, look at that bad boy. 560 feet, pretty tip, 500, 600, 700 feet for single families. Well, it's a production house, 2-story. So that's not unusual, but they're still good, right? Still good. 0.93. So let's take a look at ducts. So what these are just screenshots out of the Writes Off software. And so what this is they can go through and then pick what it is they want to use in their design. So they've got different parameters that they can use, all kinds of different stuff, and they can actually set it up per, if it's a guy that designs HVAC stuff, they can set it up per HVAC company. Well, this company likes to use this fitting, this fitting, this fitting, this fitting, so they can actually set that up. So that's all the fittings that it uses in the design. Okay. Well, this particular design used something called an 8AE. Oh, look, elbow 8AE. Well, looks like a 90-degree elbow, yeah? No, let's take a look at what that is. And so here's a picture of it, and here's what it is. So the air thinks to go from here to here, it's 10 feet long. Well, let's look at the description. Well, this is a smooth elbow with a radius by diameter of greater than 1.5. Woo. So if this were a 6-inch duct from here, if this was a 6-inch 90, this is a one-piece stamped 90 is what this is. the finest, one of the finer fittings that you can get. This would not fit in a joist bay in any way, shape, or form, right? From here to here, there's probably close to 16 inches. It's gigantic, right? What do you suppose we are normally seeing? Does it look more like this? Yeah. And these are the little gores where you can turn it. And it's usually the tightest thing that we can get, isn't it? It turns 90 degrees so quick it makes your head spin. Well, now that one's 30 feet long. So now instead of 10, every time I'm putting one of those in, it's going to be 30. It's 3 times the length. Yeah, so here to here is 10 feet, and here to here, and this one is 30 feet. The air thinks it's 30 feet long. Why? Because air is dumber than a hammer. Air is just as dumb as it can be. It loves to be told where to go. On this, it's got these nice smooth pieces, right? Comes in, told where to go, turns 90, no problem. Air comes into this bad boy, hits this gore, it gets all confused, hits this gore, it gets all confused, hits this gore, it gets all confused. So it's got a lot of turbulence going around in this fitting relative to this one. So it takes an extra 20 feet to go from here to here. Now, it's the way the air works. It's the truth. Let's look at another one that was used in this design. How about fan fitting 1P? Fan fitting 1P. Well, what does that look like? Does that look like a forced air furnace, a supply, maybe a trunk line going either direction? Does that look tip? This is where everybody's going, yeah, that looks something. So let's see what it is. 1P, it's only 20 feet long. From here to here, the air only thinks it's 20 feet long. And the beauty of it is it's got turning vanes in it. Now in commercial applications, we'd see the little turning vanes. That's what this little line is right here, these little, right? We'd see a turning vane in here. And so the air comes up, hits that turning vane and knows exactly where to go. What do we normally see? The tightest thing we can possibly make, and it's 120 feet long. We just added 100 linear feet to that ductwork in one fitting. So the air comes up without the turning vanes, and what's it doing? It gets all confused, just going, hey, what's going on? And then 120 feet later, it realizes, oh, hey guys, we could go either way. Yeah. Well, I like the 20 foot, so that's what I used in design. Because if I used the 120, it wouldn't work. How about 5K? Well, now it's a return. Well, so it could be a bottom return. That's what we've got. Bottom return in this particular case. And a 5K. Here's a beauty with vanes. You know? Now you could do the same thing. This, if you could still have a square inside, but you've got a radius outside, you could actually get some pretty good numbers here. You really, really can, okay? So I see a lot of this. That one little radius helps tremendously, rather than just square cut without any vanes at all. So how about 2JO? What is that all about? What is this? Oh, here we go. What does that look? That looks like a top takeoff, does it not? That's exactly what it looks like. So here's what it looks like. So 2JO. So what this actually is, as you can see, hopefully you can see from the picture, that let's say that this is a 6-inch duct here. It actually has about an 8 or a 10-inch takeoff bell there, and then nicely reduces it as it turns 90 degrees. Okay. So if that's what you've got, that's fine. But this is what we would normally see, is it not? Same size. If this is a 6-inch here, it's a 6-inch top takeoff, makes a very quick 90. You can see, so 2JO is at 50 feet, 2J or 2I, 65, and it kind of goes up. Well, what's that about? What? We got a 2JO, we got a 2J1, 2J2, 3, 4, 5. I wonder what that's all about. I know the answer. We'll show you later. But just remember this, what this is all about, and why do we have so many here? And why is an O 50 and a 5 80, or right 65 or 110? Oh my goodness sakes. One fitting. A 2i5 would think that this, from going from here, from this point to this point, is 110 feet long. Figure out what that is. We'll show you. Just remember that. Keep that in the back of your mind. So yeah, this is just talking about, you don't have to have a physical return air in each and every room, but you do have to have some sort of transfer air opening. Now, jumper ducts, I think I've got some pictures here later that kind of show different ways to do that. But that really cuts down on the total equivalent length. So centralized returns. So for instance, these are two returns that are coming up into here. We got one return that's coming out into the master bedroom. This is just a ranch house, basement. I don't think I got the basement on here, but the key there is that we need some sort of air movement. Now, they're going to tell you, it's like, oh, well, we undercut the door on that, Gil. We get the door cut and it goes underneath the door. Well, if somebody tells you that, email me and I'll send you the chart that says how far that's got to be cut. And believe me, if they were trying to do it in the master bedroom, they'd have a 3 or 4 inch undercut. I don't think they're going to be going for a 3 inch undercut on the door. So here, and it's kind of tough to see. I wish I had I should have taken a better picture, but so here's this piece here. Let's see. So here's an example. So we got a 2J2 here, a 2J1, and a 2JO. So don't look at any of this other stuff, but you're just looking at these three pieces here. This one, and this one. And if I knew nothing about the rest of it, which one is longer? Which one of these would be longest? Well, this one here. And this is the shortest. Why? Because air isn't particularly bright. It rushes down and then hits this trunk reduction, repressurizes it, and realizes, oh, I could come out here. So what this means is that this one has 2 takeoffs downstream. This one has 1 takeoff downstream, and this one doesn't have any. And this is why trunk reductions, like the one you see here, is so important, because it repressurizes this section of ductwork. Okay, here's another one, right? Here's a 2J3, and if you could see this one here, you can't see it, but this one's a 2J5. So is it this duct, this one, this one, this one? This one here is the longest. And look, it's what, 3 feet from the furnace. This one here added 110 feet. Yeah, because it had so many downstream. So this is why the trunk reductions are important to see on the design. And if they are in design, make sure that they're out in the field, because, right? Now, if you had 2 more, 3 more added to this bad boy, serious stuff, huh? Might not see hardly any air coming out of here. Yeah, so trunk reductions are hard. And this one's, you don't want to get an 8.5 by 11 like this, where it's all scribbling, you can't see. They can do 24 by 36s, so you can start to see stuff that's clear. Yeah, so so everybody can picture what a 4AD is, yes? Got that in your head, what a 4AD is? Yeah, which is why it's important to have pictures on the job site. But yeah, 17 feet, a 6-inch duct, right? 5-inch duct, 12 feet of it, yeah. Just a quick shot from, this is Elite. Same kind of stuff though. You need the fitting IDs. When I say, please include fitting IDs on the duct design, this is what I'm talking about, because that's how I identify them. Same thing there. So here's when I say, hey, I need pictures of the fittings used in design, okay? Well, there's a 4AD, that's what it looks like, right there. Here's a 2I, that's what it looks like. Here's a 4I, does that look familiar? And how about a 4H? Well, you got register boots, one that comes off the end, yeah, like more like a ceiling piece with a piece of flex on it, right? Turning vanes. Now, I always say, hey, please provide pictures, the pictures of the fittings used in design. And hopefully that seems kind of obvious now, because we saw one fitting that went from 20 feet to 120 feet on a fitting that they typically use, which would mean, guess what? If they use those fittings in the field, this system won't work. It won't work. It won't work as designed, that's for certain. Okay, so we won't take time to do this today, but it just is, hey, you could actually draw your own system out just like this, give us dimensions, give us, right, duct lengths, and give us some fittings here as to what's going on, and actually do the math, right? Look at the different pieces, and, you know, I'm just giving you the answers. You'll get that in the handout. I think Erica's got all of them. But you're starting to pick. You start to think, well, which supply is going to be longer? You start doing the runout length and all the different groups of fittings. Yes. Right? Then you have your friction rate worksheet. You know, you start doing the math. Yeah, this is just an example, right? It says it was 461 feet. And look, so in our example there, it didn't work. Didn't work at all. But guess what? They could change one fitting in this and get it to work. And that's this one right here. Remember that one fitting? If they use a decent fitting off the top of the furnace, they change one fitting in that entire system, it works wonderfully. Because I just went from 120 to 20. Took 100 linear feet off of it. Right? So yeah. That's the nice thing, is that even on paper, they can figure out we're in bad shape and change one fitting and we move on with life. Okay? Just a few quick picks here just for fun. It's a jumper duct that actually works for return, because it's just a return. It's just a path, you know, just a really fair path. You know, this is great. Actually, it's great for sound, but it does put more holes in the ceiling. Yeah. Not exactly the best thing, and insulated duct between the two. Does it work? Absolutely. The code doesn't say anything about it, right? Put an R8 in the duct and we're in good shape. This is an early one that didn't last very long. Does it work? Absolutely. It works just fine. Okay? As long, you know, if this is the bedroom back here, this is the hallway, say, and it's where the return air is at. Air is going to flow through there just fine, no problem. Problem is that it doesn't do much for sound, right? Yeah, it doesn't provide a lot of privacy in the rooms, which folks seem to like. But they do make a lot of different of these ducts. Transfer air ducts that actually got some insulation in it, does great sound, has great soundproofing qualities, but the air moves right through it. Here's another example that actually works. More like the old building cavity return airs, although that's not what this is. It's just relief air. That's all it is. So you got a little plaster ring there at the top and the bottom. The relief air goes from one place to the other, and we're in good shape. That works too. Duct testing is a piece of cake. Not hard to do at all. But is not required unless some of either the furnace or any of the ductwork itself is located outside the building thermal envelope. If none of that, then you don't have to test it. I encourage everybody to test their ductwork for total duct leakage, but it's not required. Static pressure test, again, as long as you've got the equipment. Not hard. You're putting your probe in the return there, putting a probe in. Looks like they got it below the coil on this one, which is good. It's measuring the static on the coil too. And then a digital manometer is telling us what's going on. Here, you just basically add those numbers together. And that's about a 0.35, 0.34. This thing's singing. This thing is moving wonderful stuff. That's a beauty. And that's an old one. Gosh, that's got to be a 20-year-old picture. 15 for sure. No longer than that. Flow hoods. This is CFM, room-to-room CFMs. Okay. Right. Put the hood down. Read the CFM that it's telling you, and you move on with life. Right? Again, not really a code requirement, but I encouraged it hopefully and actually required it in the very beginning, especially in first-time builds. First-time models, if you're going to build it the same way over and over again, well, let's make sure the first one works. How about that? This is a Magna Helix gauge. This is actually measuring static pressure. It's called a Magna Helix gauge. People still got them. It's just that the digital ones have kind of taken over. You just have to set it every time you use it, and you have to hold it relatively level. What we're doing here is we're measuring what we call room-to-room pressure. So this is a bedroom in here, and it's just got up above there one of the relief airs, or it could be a master bedroom that's got a designated return air to it. What we're looking for is the pressure that's within the room. I guess this will have a relief air because the return air is where we're standing outside the building or standing outside the room. We'd like to be within somewhere around plus or minus 3 pascals. So I've been talking about pascals, haven't I? Have I told you what a pascal is? So what is a pascal? Well, a pascal is a measurement of pressure. So 1 Pascal, if you were to take your hand and on the back of your hand, you would lay one of those really tiny Post-it notes, the ones that are about 3/4 of an inch square, and you laid it on the back of your hand, right on the hair on the back of your hand, that would be about 1 Pascal of pressure. Yeah, we hardly know a Pascal. Air knows a Pascal like you would not believe, okay? But this just is a nice design thing. It's a best practice. Nothing in the code, nothing at all that you have to worry about, but is a good design practice. This way, you know, you're not getting too much pressurized in the room, so you're not pushing air through the walls, right, into the thermal envelope you don't want, or too negative because, well, you don't want it sucking through the walls either, right? So that's really all that is. Yeah, questions on duct design. So this is a good time for questions if you've got any in while that's happening. This is an old picture, way old, 25 years maybe. Back when they first started thinking about, you know, 2 system designs and putting 90% furnaces in attics. Okay? Well, we all know that this is a condensing appliance. Okay? It's got a condensate drain that comes off of it, especially if it's got an AC coil on it. This one doesn't currently, but they were having issues because guess what? Water freezes when it gets cold. They were having a heck of a time with these condensate drains and the furnaces themselves freezing. So I walked in and doing this inspection, and they had added this piece right here. This is a supply air duct. And they're like, well, Gil, we're not done. We're going to actually extend it down so it actually heats this pipe. I said, guys, you're trying to heat the attic? This is a vented attic. It's never going to happen, guys. Give me a break. Oh, yeah, I guess you're right. So what am I great? It's awesome. They were trying. They were trying. Anyway, that's what I got. Do not hesitate. Email me with questions. If you got questions, give me an email, give me a question. If you're just embarking on doing Manual J reviews, do not hesitate and send me a review, send me questions. I can walk through it pretty quickly with you because the more you do, the more you learn and the less you'll need me, right? Pretty cool stuff. All right, so questions. Do we have any answers? No answers? No questions? Come on, got to be at least one.
Yeah, it doesn't look like there's any Q&A for us today, Gil.
Well, that's because I do such a great job.
Yeah, you're just so thorough.
That's it.
Oh, we got one.
Right.
And do you have any thoughts on ducted minis?
Ducted mini
Yes.
splits. Well, they are going to be kind of a manufacturer piece, yes, because they've done their own testing. Don't know. I don't think I've ever seen. I've seen a lot of people want to put in mini splits, but they weren't ducted mini splits. So essentially, for those of you, a ducted mini split is right air source heat pump generally, and you can usually just heat it like for a room. Okay, in this particular case, you can actually get mini splits that then are ducted to different rooms. That's a good question, Rebecca. I'd have to look, but as I understand, the manufacturers have done testing on that. Now they may have design parameters because it's all going to be based on their fan curve chart on maximum statics, right? In which case they may, because a lot of those are not metal pipes, a lot of those are plastic, yeah? Yeah, a lot of those are plastic, yeah. Oh, meeting together with Mitsubishi. Oh, wonderful. Rebecca, I'd love to hear what you've got. That'd be great. Yeah, Mitsubishi puts out a lot of them, clearly. Probably the leader in ducted or mini splits themselves. They put in a lot. So yeah, that would be wonderful. Whatever you learned today, I would love to hear it. Because I'm no expert there. I'd have to research it just like anybody else, right? And then we've got, looks like James, good old James. What are your thoughts on undercut doors for air transfer as returns? Is that good? Hey, if you, James, send me an email and I'll send you the chart right out of Manual D that tells you what you have to have as far as an undercut is concerned, based on the CFM within that room. And I can tell you the gap is gigantic, right? It's huge, relatively big. It's bigger than you think. The problem is that, and it's not a problem, is that number one, it has to be really big, right? Number two, you end up with what they call ghosting, okay? And a lot of times these doors are, have carpet underneath them, yes? And if the gap isn't big enough, or even if it is, it has a tendency for all the dust and everything that kind of goes through there, the dust we can't see, the carpet's a really good air filter and it catches all the dirt. And you end up, when you open up the door, you end up with that ghosting of that dark line underneath the door. Well, that's just the dirt that's gotten filtered out because, air's trying to get out. And it's got to go through the carpet. So that's kind of the other issue that goes along with that. But James, I'm no, and neither is Manual D. Is not a big fan of door undercuts. Anyway, send me an email. I'll send you that. It'll be good. Cool. All right.
All right, that looks like all the questions. Gil and I will stay on the line for another minute, but thank you, Gil, and thank you to everyone for attending today, and have a happy holiday.
Yeah, happy New Year, Merry Christmas, all that stuff.